it's a slow growth and it's basket of energy, not one. One energy source will not be. Okay, we have to have it. And we cannot wait to grow all the things. So what other option we have in case of fossil? It's nothing bad with that. They brought lot of progress because of that. If you remember, coal was the first thing we realized before wood burning. Right? Energy source, what was becoming coal, alright? And then we moved to oil, and then we realized gas also can be used. So why we moved from wood to coal? Can you tell me? Long back we are using wood, and almost entire world was wood, and then we invented on coal, and we thought it's better. So why we moved from wood to coal? Heating value, that's the weakness. So now 10 ton of wood versus 5 or 4 ton of coal. So density, energy density is the key in energy. Now coal has 33 megajoule per kg, and we moved to oil. We found oil and we jumped on oil. Coal didn't go out, but oil picked up. So why we moved to oil? What was the thing? Why we started a lot of oil, jumped on everything built around oil when coal is there. Energy density and one more thing. If you remember, trains, a steam engine, then we moved to diesel engines. Now electric. Alright, that's the transition, coal, oil to electricity now. So from coal to oil, there is one more thing which very, very easy or useful is being liquid. If you have liquid, you can transport pipeline across the countries, across the continent. Coal, how transportation happen? Truck or train. Now you can found something which can be pumped and we say higher energy density. So why will not be picked up? Alright, so that's why we move everything on oil side. And then we started realizing this emission issue, environmental conscious issue. So that's the thing. So now oil or coal is not going to go away. Nothing magic is going to happen. It will take time. So can we do better with that, keeping them? So the issue is if we use fossil fuel, we emit CO2. Can we make that fully oxidized carbon compound to some use? The shifted pollution from non-point to point. Now can we use that point pollution to our benefit? Next something. Just carbon capture. We can capture CO2, one work is done. Now capture is not enough. Only thing is you need, but what to do once you capture it? You have two options. You sequester it, bury it somewhere, or make something of it. So it stays inside, but still you are using. So you increase the have this first non-point all over, but see you make it to something here and the pattern here is fine as long as you capture. Okay, so tree grow or biological sequestration you can do, forestation you can do, that's a natural one, and then you capture, put inside coal mines, depleted oil resources, you can find a way. You can inject it, but a study comes what the impact, long-term impact of all these things, and you will see that everything what we are suggesting, they are all associated with, and PEA has to be in place. Techno-economic analysis has to be in place. Otherwise, you can make all the ideal things, nothing will be achieved. So a lot of focus on carbon sequestration, capture and sequestration, or there are many different sectors, residential, industrial, agriculture, and which one emits most? Anthropogenic, human. Which activity emits more CO2? More. Energy use. Okay, that's the highest. That's why focus is on electrification and other things. So you can say global carbon different where you can see how it moves different way. But there are natural sources of CO2 also. Ocean atmosphere exchange. Carbon dioxide solubility, which you get in ocean based on alkalinity and other things. So that gas and water interface exchange happens. Plant and animal respiration, they contribute to it. The animals contribute to mechanical emission. Soil respiration and decomposition. Organic. So these are the major sources of CO2 emission. And you see that they are perfect. Carbon capture I was talking covered, and there are two ways. Theoretical carbon sequestration you can do to sequestering below the earth, or biological carbon capture by growing algae. To grow algae captures carbon, and I was talking we know how it blooms. Can we control that bloom, and then we can grow it. So that's one. We already talked about this, how CO2 emission gone over the time, alright? And you will see that mostly happened in 1940, 50 and started growing and emission gone high. And then mainly we learned around that time fossil fuel use gone high. Fuel, FEW, again you have to remember. More we secure fuel, more developed we are. That means we are using more food, more energy, more water. And that through all the industrialization happened, getting better, it started. And more energy use is directly linked with more CO2 emission. So agriculture is one of the major, and transportation, industry, these are the major sectors where CO2 emission happens. Right? Agriculture, electricity, transportation. So you will see that electricity is getting more renewable, getting better. Electricity being used instead of diesel in agriculture, getting better. Right? Transportation getting more electrified, getting better. So these are the sectors and how to address that. That's the problem. Can we capture dispersed residential non-form CO2 emission? We are talking carbon capture. Can we capture non-dispersed? Dispersed basically. We can design capture process. I'll tell you about the process. It's very difficult to design for this building, that building, that building, that car and all. Alright? So the point is, can we make dispersed to point? And then it is better to work. So CCS is practical. Carbon capture is practical only where we have more or most concentrated CO2 emission. And tell me few sectors where you have more CO2 emission. Power plants, coal power plants. Alright? What else? Can you tell me another industry which emits a lot of CO2? Cement. If you look at the cement making process, calcination where you need, so you keep. Steel, coke, petrochemical plants, blast furnaces, nitrogen fertilizers, ammonia. I'll change the topic. You know how ammonia is made and what's the use of it and how intense CO2 emission is. You won't believe fertilizer takes a lot of emissions. Anyone knows how fertilizer is made? Urea. How we get urea? We buy it, put it, but how urea is made? Yeah. How urea is made, and when urea was not there, how fertilizer was there. So urea brought revolution in agriculture because we could supply nitrogen in the form of urea a lot. Alright? There is very high percentage of nitrogen in air, but we cannot keep it and give it there. Alright? It's a discourse. So urea brought a compound where you have a lot of nitrogen and which can be handled easily. And that's the thing. So how urea? Urea is made from ammonia and CO2. That process well established. You will see many fertilizer plants. Okay, so ammonia and CO2 pressurized reaction gives you urea. So you one place of CO2 here, right? How ammonia is made? So how much fertilizer you can think of? Everywhere you need fertilizer. Garden to big farm to everywhere, right? So if you can cut down that area, a lot of CO2 capturing will happen. Impactful. So how ammonia is made? Ammonia is made by Haber-Bosch process. Okay? So you take nitrogen from air and hydrogen. How do you get? Because you need N and H. N2, H2 will make ammonia. So nitrogen you can get from air. How do you get hydrogen? How ammonia is made? That's my question. So you have nitrogen source, you will take air and it goes to air separation unit and you get nitrogen. That's how you get nitrogen cylinders and all that comes from ASU and air separation unit. And then they need hydrogen connect and get ammonia. So how you get hydrogen? One way is green hydrogen electrolysis, which is coming up. It's not there. So how you get hydrogen there? It's a natural gas, fossil fuel. Okay, a steam reforming of natural gas. Methane gas reformed to hydrogen, and that's fossil fuel. So that's how we make ammonia to urea, and you see urea used like a transportation sector fuel used. Agriculture fuel is urea. Alright, so that much hydrogen is used using fossil fuel. So can we find making ammonia differently using green hydrogen instead of fossil hydrogen? That will have a big impact on carbon sequestration or reduction of CO2 emission. So these are the places. That's why it's a nitrogen fertilizer plant. And it's very difficult to connect if you don't know the process. Why you are talking CO2 in ammonia production. Right? So if you look at deeper, you will find out who are the bigger emitters. So fertilizer does two things. One is runoff. You spray runoff, nitrogen, NPK using water, LG blooms, and the other thing is CO2 emission where they are production. So LCA of fertilizer will say it will look not very healthy. Now we are talking about carbon capture sequestration, and again I say you need to find concentrated places. You will feel good, we can feel good about it, we are capturing, but it won't be impactful. If you design for one building, one house and all. So the major point sources are power plants, steel, cement, where you have a lot of CO2. But how much CO2 they have? Let's come to coal plant. Coal to electricity. We burn coal, get electricity, Have anyone visited a power plant? Coal to electricity? So what are the waste generated at coal power plant? Fly ash. You burn coal and high ash content in coal will left as a fly ash, and that's a mountain of fly ash. It's not 1 ton or something. It's like a mountain. Go and visit and you'll see that fly ash is a bigger issue. It has a lot of metal. That's why it's one of the dirtiest fuel is coal. Okay, so electricity, and then CO2. So if you look at combustion, coal burning will give CO2, but if you go to gas composition, go to a stack, take gas sample and analyze how much CO2 you will find. We are talking CO2, but if you take a sample, how much CO2 you will find percentage wise? 6 to 8%. 7 to 10, 3, 11, 12 different places, but in that range. So it's called flue gas coming out of the stack, and the concentration is 6 to 8%. So you have a large column and a small proportion of CO2, but still it is concentrated than air. Air is 400 ppm. So it's a good place to start here. Okay. Now again I will come back to electricity production. So coal combustion. So for combustion, what we use there in case of coal? How you burn coal?
Furnace.
Yeah, but furnace is there. How you burn it? What you need? What you need for fire? Oxygen. Right? You need air. So when you do air, what you get with air? What is the most? If you do air analysis, composition analysis, what is most in air? Oxygen. Nitrogen. If you do combustion, and nitrogen you don't need. Alright? Nitrogen is just like a luggage, it will come. And that will dilute your gas composition, it comes out. So when you have 7 to 10 or 12% of CO2, what is the rest? Nitrogen is didn't do anything. It's like inert, maybe some oxides, some water vapor. Okay. So now we are trying to design a process where CO2 capture can happen here, but it is less concentrated. Let's say they started burning coal in this plant, thermal plants, using oxygen. Then how this composition will look like? Coal-fired plant, you started using oxygen. Then how this composition will look like? What is CO2 and water vapor? Because combustion is hydrogen will give you water, C will give you CO2. So now this becomes much more concentrated and cleaner. So carbon capture is easier, it's much more pure. Looks wonderful solution. Why not we do that? I keep confusing you. So why don't we do that? Because oxygen is not free. Move from here to here, create another thing. So remember TEA and LCA, techno-economic. Go to coal power plant and tell them why don't you use oxygen here? Let's do oxygen, it will be much cleaner, and they will look at this and will pay for the oxygen. Alright? So techno-economically becomes challenging. Oxygen is not free, hydrogen is not free. So you have to produce it. So air separation. So then you look at this carbon capture is easier. So oxy-fuel combustion, that process is called oxy-fuel combustion. We use oxygen. It has a lot of merit, but again it's business and other things will have it. So that's Otherwise, you have to develop a solution where you can remove CO2, concentrate in a way, and then you can sequester or utilize it of later. So option for capture of CO2 from fossil fuel plant, I already talked about what are the different options. Flue gas after normal combustion. Yes, from a step you can capture, you have a good separation method, you can do that. Flue gases after combustion of fuel is pure oxygen. That's the best option, but can be net economically higher. Okay? We get oxygen cylinder, we buy oxygen. So oxygen is produced, we know that. But can we use that oxygen to that big a scale of combustion? So techno-economically, so you have to choose a path, go this one or this one or this one or this one. Prior to combustion during the gasification of coal, you can gasify coal itself and capture CO2 before. We'll talk about gasification. You can gasify coal and carbon monoxide and CO2 is produced, CO2 you can remove. Or during the operation of fuel cell using fossil fuel, that's a separate. So there are different options and economics beside. There is nothing which we don't know. All these processes are well known how to capture CO2. All the economics and life cycle assessment makes us difficult to do. So basic approaches and CO2 capture for power plants, fuel, air, CO2 containing flue gas, CO2 capture and CO2 for storage. That's one. Oxy-fuel combustion, fuel and oxygen. The smart thing is not showing air separation here. Okay, that's a cost, but this is and CO2 storage. This is much more purer concentrated. Big combustion capture, fuel and oxygen air combustion making carbon monoxide, not CO2, and separate CO2 from here before and then move. So there are multiple options of carbon capture storage when we go for point stores and carbon capture utilization and storage. We talked about these things. So CCUS is direct air capture. What is direct air capture? That's one biological way of doing sequestering carbon. And you will hear a lot nowadays it's becoming more and more common to talk about why don't we do for that. Direct air capture. So what is the concentration of CO2 in air? Anyone remembers? 426, 427 parts per million, milligram per liter. And I was talking that we have 7 or 8 or 10% of CO2 in power plant, and that is dilute. Now I am saying direct air capture, which is not even a percent, and we are saying we can capture from there. Alright? So again, no, that's another way of capturing. Power plant units, they can do that, but direct air capture gives you benefit where you can capture anywhere now. You don't have to locate next to the power plant. You can develop, it can be a small scale also, disperse. You can capture. So direct air capture, I will talk more how it is done, but you can capture CO2 in certain solution, it lights the CO2 and you can power generation, cement, iron, all these places we can capture.
In case of carbon, porous carbon, granular or powder carbon, at which concentration it might have higher absorption rate of these mineral gas.
So again, the greenhouse gas and CO2 we are talking.
Majorly CO2.
So
CO2, at which concentration we might have optimal.
so higher the concentration, better is the absorption.
At atmospheric levels are certain areas like where most of the organic, decomposable organic waste is going to down, nearby landfill sites, or nearby any combustion municipal dumping areas. So at such conditions, we will have more CO2 emission. So will it be possible to use carbon as a absorbent material to at least minimize the local pollution?
Yeah, definitely carbon can work as a absorbent there, porous carbon. चलो
But you need to again compress the air.
you have
without compression. Compression is without giving
it's like investment on yeah, repeated job.
again that is energy.
You can put solar for that, and there are some use solar for crystallization, and you can do that. Yeah.
Without suction, it will be possible to capture then becomes
Yeah, so again you will have to modify carbon surface properties. This element. So that's surface chemistry of carbon how can. So you will see many people that start working with certain things and
Absorption, desorption.
yeah, but that's a good one. So carbon capture, utilization and sequestration. So utilization what we added. Can be utilized and then sequestered. Can be use CO2 for certain purpose. So CO2 capture in chemicals, ammonia like CO2. So you can pass CO2 through gases to ammonia. And then you are done. Now you can dissolve it using heat, and now you will get a pure stream of CO2 after desorption. And CO2 cylinder has many uses. Tell me one good example of CO2 use where we use CO2. CO2, where we use it, it's not always bad. Okay? Where you use CO2? Pardon? Fire extinguisher, yeah. Some more. Soft drinks, Pepsi, Cola, and all. Yeah, you do that, right? Where we produce pure CO2. I talked about those diluted CO2 mixed with flue gases. Flue gas means mixture of nitrogen and other gases. Where we produce pure CO2. You know? Ethanol plants. So ethanol process, when we will be discussing, there is a process called fermentation. And when you do fermentation, you get alcohol and CO2 comes out. That's it. Okay, so ethanol production is another good thing that you have a pure CO2 which can be used. So in general we say you need CO2, no. That's a pure CO2 you can use for certain things. And CO2 have many chemical use also in bioplastics and many other carbonation reaction we do that. Ammonium, CO2 capture in iron and steel, you can do that. CO2 capture in cement industry, we talked about that. CO2 in fuel production. So wherever you can do, you can capture, you can transport, you can put in a storage or in use. The storage is below the earth somewhere, but enhanced for oil refinery, recovery, depleted oil and gas reservoir. Oil reservoir has been used, so you can pump CO2 and it enhances. But CO2 has used, I was talking about urea, right? Ammonia plus CO2 will give you urea. So now, we capture CO2 here in ammonia solution, we release CO2, that can be connected here to get urea. So I capture for some time, right? Concrete plating. Concrete is carbonate, you can do that in urea. Methanol, you can make methanol from CO2. There is a reaction again we'll talk down the line. Synthetic methane, liquid hydrocarbons, we'll talk down the line. These are the ways CO2 we captured. Now you don't have to always sequester below the earth, geological sequestration. You can lock in different chemicals. Have you heard about bioenergy? When you make biomass, you will end up getting some biochar and some soil residue that can go on shore. And this direct air capture can work from solar. You need electricity. So wherever you need electricity, we are definitely reducing CO2 emission using renewable. So these are the ways CO2 is not only neutral, sequestration also. There is difference between neutral and negative. Neutral means you took it and put it back. Negative means you took it, put a little bit down also, so it's negative, carbon negative. So there are different ways. Nature-based solution, tree always helps, right? Many different ways. They give rules, they do, and they do magic with CO2. So cutting tree is not good. And so afforestation, replenish forest, nature-based solution. Land management, technology-based solution, DECCS or direct air capture. So direct air capture, you pass through chemicals and it will capture and you can reach it. Pulp mill for power paper production. So pulp mill, how pulp is made? Have you ever thought about that? How paper is made? They logs, right? 3 logs, and you use only fibers of that. Use for paper. What happens to other things? Talk down the line, that's the waste. Okay, can be used towards that will make better results. Okay. Biorefineries, not just focusing on ethanol, putting some more products in that will help. So direct air capture, this cost is nice, but 95 per ton of CO2, it needs to come down. So flue gas, power plant, or direct air capture, or many other places where we need to capture CO2, there are 4 fundamental technology which you can use. Okay? The first one comes with absorption. You can have a liquid or ammonium solution. Monoethylene, NA is most common, many industries use it. Pass through gases, ammonia like nitrogen compounds like CO2, which keeps it, absorbs it, and then you have to dissolve it. So absorption process is the number one. You can do that. The other one is physically you can do that. High CO2, but you need high CO2 concentration. Economics. Very dilute cannot be economic. This is good for low CO2 concentration. High is always good, but you can work at low also. Absorption, but you are talking activated carbon or zeolite or many other things you can pass CO2, it can absorb. Membranes you can do, and liquefaction. You take flue gas and you liquefy, and then you can separate it. How can you liquefy flue gas or CO2? So dissolving absorption.
We need to be compression system where we can reduce the temperature.
Yeah, so that process is goes in cryogenic range. So cryogenic cooling, very low temperature. There. So again I am coming that all these things cost energy. The winner will be which cost less energy, safer handling, easier handling. Okay. So CO2 capture can be done, separation and capture, absorption, cryogenic and membrane. This is liquefaction, membrane, you know that means separation. You can pass through membranes. What is the issue with membranes then? Very classic system, you pass in membrane, but it fouls. Because flue gases are not pure. You have nitrogen, you have some contamination and many other things. Absorption, chemical based processes, physical absorption and chemical absorption. The NA caustic solution, these are the solvents, you can do that. Absorption, physical, alumina, zeolite, or calcium oxide, chemical, because it will carbonate and it can leak again, CO2 come out. Cryogenic is very low temperatures, useful but high-end applications, where you can afford that much cost. Membrane, gas separation, people are working. So that's why you already talked. No matter what you do, energy is required, and meaner will be lower cost. And you look at the deeper, LCA will be the better option. Here you have it. Absorption system, MEA I already talked, Selectron is physical absorption. So I don't want to repeat many of things I already talked. So, CO2 absorption technology, ionic liquid, you know ionic liquid. These are liquid which has very low vapor pressure. Okay, so that also used for doing this. But these are costly. That's why there is no cost here because it's coming up here. These are relative cost. You don't have to look at this is the final cost. These are the published cost and it can be converted. But calcium looking micro etching. We will have a separate lecture on micro etching, but micro etching needs CO2, so you can use micro etching application next to power plant. You can do that. Flue gas can go through, you capture it, you use more fuel protein. Ammonia, fuel cell, microbial fuel cell. So energy consumption you will see and the linear will be lower NDA. So you will see many power plants or petrochemical industry they are using NDA already. Government regulation will come cut down emission. We have built such a huge plant without doing that. Now government says, our policy says, cut down. There is a cost to bringing a new process and there is a cost to retrofit. You are not going to dismantle plant and make net new. So you have to build another retrofit next to it. There may not be a land and a space, there may be many other complexity. And do you have to shut down the plant to build it? All those things. So it looks simpler, but it becomes more complex. So CO2 we are talking. So CO2 properties are, you can see that this is a picture point. Solid, liquid, gas in all three phases it happens. Okay. And these are the critical points. So below critical point again you can have it. So it's a thermodynamic diagram. And knowing this, you say there it will be high, there it will be gas, there it will be solid. So large scale silica, I already told zeolite, molecular sheet, metal, ceramic, there you can do CO2 absorption. So this is typical power plant load diagram. Okay. Catalytic reduction, we did boiler, flue gases coming, some active gases reduced to stable. ESP, electrostatic precipitator, is separate particulate matters, gas is cleaner, two gases coming up. Now you need to concentrate. So you cool it and then CO2 separation happens. And it's a multiple stage and CO2 mix can go out and you can emit it or you can capture from here. So again, simple, but running power plant, you have to add this. That's the cost and retrofitting, how to repeat and how, at what stage of this plant is end of life or started. Another option is integrated gasification combined cycle, IGCC. So again, let's talk about efficiency. It's all about efficiency. You have a heating value and how much you can transmit for the work. So coal-fired plants, efficiency in terms of electricity, how much coal you use, how much electricity you produce, efficiency, how much anyone. Very good power plants is 35, 36, 33% of efficiency. Okay. What does it mean? 2/3 is best. Only 1/3 of heating value or efficiency we would capitalize. Thermodynamically, we know 100% is not a possible efficiency, but can be increased from 33 to certain percentage. Again, that is thermodynamics, but can be changed with better reactions such that we have. So, lot of work going on. Why it is important to change the efficiency? Why it's typically important to improve the efficiency? You reduce, even if you depend on coal, you need less coal to get that. So you reduce CO2 emission per kilowatt hour of electricity. Alright? So the concept is another came out with the coal power plants, thermal power plants. One is CO2 sequestration capture using amine solution NEA. Another is further improve the efficiency using IGCC, integrated gasification combined cycle. So I will let you read this, but I will show this picture. So in power plants, we have lot of waste heat also. We get electricity, but when you do combustion, lot of heat generated, and we don't use that heat. Not very efficiently. So you can combine the exhaust heat to get another steam plant. So you are getting electricity additional. Without IGCC, you are like this. And gases are coming from a stack, they are hot. 200, 300 degrees. Can we use that heat, recover heat, additional heat, you can keep it heat for electricity. So now you improve the efficiency, that is called IGCC. Improving efficiency gone up to 45%. IGCC plant, those thermal plants, they have IGCC, they have increased efficiency. Everyone benefited, themselves also. Base coal needed for the same amount of electricity. And that's indirectly or directly CO2 capture. So here the energy analysis, you will see that retrofitting existing power plants. Retrofitting means without changing, you just replace one thing, put this one. That's possible. But that plant is not designed for it, but designed for something, and now you have to retrofit. Even the taking shutdown is a cost. Then there are many other costs, and you will see that as now you will appreciate the challenges of capturing. In classroom and all, it looks nice, you can capture. When you go to industry, it looks real, you will fight with them, it's tussle with that. Why don't you reduce, then why don't you put some grant, loan and other things. Yeah, that's one example. Efficiency benefits. For example, 80% of CO2 in the earth captured, but the efficiency of power plants dropped from 40 to 25%. Then we need 1.14 times more fuel. That's how efficiency plays. So efficiency needs to be improved all the time. Car driving mileage needs to improve. Bigger car, less mileage. But even the same company for bigger car, they are working towards improving the mileage. So efficiency is a constant contribution of improve. So this is directly a capture. If you have CO2 and you have an NOx solution, caustic solution, what you do that? You put a fan, full of air, pass through NO, caustic solution, it becomes NOx and you can regenerate it. That's a direct air capture. And the effect chemistry NOx solution dissolves sodium carbonate, sodium is replaced by calcium, become calcium carbonate, simple chemistry, and calcium carbonate you heat again and get calcium CO2 out. Compression is another way you can compress your topping, you can get CO2 out. Liquefaction, we already talked, cryogenic, go very low temperature, you can liquefy. Look at the flow thermodynamic pressure temperature diagram, you see where it will liquefy. Where you dispose. One option is CCUS, carbon capture, utilization and sequestration. So utilization making methanol or growing LG, and thus sequestration means taking out of our soil for a long time, put below the earth. So you have to build a pipeline, power plant is here, sequestration site here is about 100 miles away. So the transportation comes, how you transport. Even if you capture in an in solution regenerated pure CO2, you have to sequester. If you cannot utilize, then you have transportation cost and then put in the aerosol. So there are desalination paper, depleted oil and gas field, where you can sequester. Active oil field, if you pump CO2 in active oil field, it brings oil production at high. It's called enhanced oil refinery. And recovery. Coal base, injection below the oil in ocean floor. So these are the different options. Lot of research has been done, lot of data has been generated. Comes down to what can be adopted, how much can be adopted. This is relatively new, means nothing new, but is getting more attention. It's called CCR, CO2 capture and reduction. So till now we are talking MEA solution, mono-ethylene solution, amine solution. You can capture, you can do that. And then we are taking CO2 to making ethanol at a separate place. To capture and utilize at two different places. Can we have something which absorbs, captures, and at the same time it does reaction to make methanol or something? That's called dual functional material. Okay, PCR. CO2 capture and reduction. Why we are seeing reduction? Well, if you want to make anything from CO2, you have to reduce it. This is most oxidized form. You have to reduce it. Little bit reduction will help you making some chemicals. So if you have captured, if you have a material, a catalyst or ionic liquid or something like that, where you captured and it does reaction also, that's the way to, we think it's a better way to go. Instead of sequestration, capturing here, utilizing there. So transportation, sequestering that far, that's different. The dual functional material are getting attention. If you are looking for research, this is another good topic. Look at materials which has capture and reduction both. There are DFM, dual functional material, nickel-based calcium oxide, alumina, and nickel-based. You will see that nickel are the most used catalyst in industry, and they can do that. So these are the dual functional material, and assessment you can see, but CO2 plus methane, you have to, let's say biogas. What is biogas? Have you seen digesters? Anaerobic digester. Takes organic material, change into biogas. What is biogas? Biogas is not only methane, definitely methane. Methane plus CO2. 60-40 ratio, I'm taking average, sometimes 65-56%. 60% methane, 40% CO2. Both are two ends. One is fully oxidized, one is fully reduced. Some sulfur and other things will come. So if you have sulfur, H2S and few other gases will come. Siloxane and other thing, but the major composition of biogas is methane and CO2. Both are greenhouse gas. Okay, both are very difficult to react. Stable compounds. So the process is called dry deforming. You go to 800-900 degree mix together, they will turn into carbon monoxide and hydrogen. So in biogas plant, typically how we use methane, we try to separate sulfur, hydrogen sulfide, and capture CO2 in the place you can capture there. Okay.
How much energy is required to have this?
This one, this is done at 800 to 900 degrees Celsius. So the research part is, can we have a catalyst here, electrocatalyst, which can do at much lower temperature. Okay. Then there are legal issues. I will stop in a minute. There are legal issues. Solve technical issues. There are legal issues. How to trade CO2. Okay, we have to do that. Rigorous regulatory, how to put regulations across the board. So these are complex. So next lecture I will start from here where we captures each thing. Absorption, membrane and all those ways we capture CO2, how to utilize. We will start with how can we turn CO2 into chemicals. So I think it's 4 o'clock. You can continue. Okay. One, I talked about the European beverages, soft drink. Okay. There are many other things can be done. Can we use CO2 for making chemicals? So you can make methanol out of it. Okay. If you can reduce CO2, reduction means adding hydrogen, reaction with hydrogen. So CO2 and hydrogen is a net. You can use CO2 in ammonia production. We can integrate that. There are processes where have shown that dimethyl ether is a chemical which can react using CO2. In fact, we can make CO2 and hydrogen when we are talking gasification process. I will tell you a gas called synthesis gas, syngas. That is carbon monoxide and hydrogen. So the pressure is, can we take CO2 and make carbon monoxide? If you can make carbon monoxide and add with hydrogen, let's say green hydrogen, then carbon monoxide and hydrogen can go to Fischer-Tropsch process and give you a bit fuel. So that's the way you can use CO2 and H2, go through catalytic process and you can get it. So if you liquid fuel means the gasoline, petrol, diesel. So carbon sequestration, just to summarize, you have oceanic, terrestrial, geological, mineral. Oceanic means ocean always have exchange with air, right? Gas and liquid exchange. So naturally yes, you can get it. Terrestrial is plant based. Geological means real sequestration. Minerals mean mineralization, putting in sodium oxide with CO2 or minerals. Ocean depth, carbon capture, terrestrial we talk, oil and vegetation. Oil stores carbon. When we grow plants, we see upper part, the roots contribute to carbon sequestration. It's not only photosynthesis, and we harvest, reaches, that's why when we harvest, we need some water. Geological, I already talked. Mineral, basically carbonation process. You can add CO2 and carbonation process. It can be direct or indirect. Clean coal technology. I said that coal is not going to go away. How we can make it better? Can we have clean coal technology? Clean coal means less CO2 impact, volumic impact, kilowatt hour. Okay, so there are different processes. Coal beneficiation is cleaning coal, coal blending with biomass or something, coal liquefaction, liquefy and then using underground coal gasification before bringing coal out, you gasify and bring only carbon monoxide. Combustion pathway changing, oxy fuel, air, you can do that. Post burning, carbon capture and all. So these are the way we can make cleaner. Okay. Interesting because I have already talked about them when we are discussing. There are different projects in US, UK, India, UK, US and India collaborating in many things. Tata Chemicals in one. UK, lot of universities, we are collaborating, making progress in that direction. DSP, putting lot of proposals and projects in this area. These are the projects. I think they funded 20 projects in last 5 years on CCUS and all. One was IC3 or some projects in India there. So these are the project details. This is Mumbai, a startup. They showed that CO2 capture using a new catalyst. How we do it. So these are the research directions. Reliance is working on CO2 capture. There are different ways they are doing. They have a target for that. One of those is electrical irrigation, solar, and other different. They have a big focus on LG also. Big bonds they have and looking at LG fuel and protein. DSP DBT projects. This is in US, one of the project coming up. So I'll stop on carbon capture and sequestration. The concept I wanted to pass you: how to capture CO2, dilute versus concentrated CO2, biological, geological, mineral based capturing CO2, capture to utilization of CO2 making capture, or simple sequestration. Sequestration requires capture and transportation, then sequestration. Utilization requires can you make something from CO2. Okay, these are the concepts. And the take home message is absorption, membrane, and absorption, membrane, and fraction fragility. Okay, so these are the 4 ways you can do that. And each area brings you lot of research opportunities and direction, whatever you like. Catalyst development, materials development. I talked about dual function materials. It's exciting. Capture in this material and then do reactions here itself. So you don't have to separate sequestration and so on. So these are the exciting area and definitely contribute to renewable in any direction and more than. So again the topic now, we go to the next